Hello and welcome. Today we are going to present our capstone project for the Data Science Lab course for Spring 22. The title of our project goes Electrical Power Systems, Exploring Smart Grids Through Data Science. The electric grid is directly associated with our daily lives and the nation's economy. It is often described as one of the greatest engineering achievements of the 20th century. Every year, the power system is generating, transmitting, and consuming $450 billion worth of electricity. It is a highly reliable system and a major success story for optimization, with almost every available optimization technique being used in running the power grid. Now, unfortunately, the electricity grid is changing. As the world transitions towards a completely sustainable space, there are paradigm shifts happening within the electric grid, like introduction of renewable energy sources on the generation side and complex loads like EVs on the consumer end. The traditional grid is not ready to meet the growing electricity needs of our digital economy, nor is it ready to meet the complex challenges brought on by widespread adoption of distributed energy resources, the electrification of transportation, and increased customer choice. Our grid must be made more resilient. Protection of the nation's power delivery system from cyber and physical attacks and from extreme weather events and natural disasters comes parallel to it. Factors like load volatility and power quality issues caused by intermittency of renewable energy sources like solar and wind are further topics that can be addressed. Learning mechanisms come into a prominent role here under several umbrellas, including optimal flow of power, electricity market trends, load forecasting, and of course, maintaining the stability and resiliency of the grid. Achieving this resilience is essential, even as we attain higher standards of performance and reliability, cost of service, efficiency, environmental impact, and most importantly, safety. Now, the American electricity grid operates at a frequency of 60 hertz. Maintaining a consistent electrical frequency is important because multiple frequencies cannot operate alongside each other without damaging the connected equipments. This frequency is just one of the numerous factors affecting the stability of the grid. Largely, the stability is determined by the supply-demand balance. A closer and better analysis of grid parameters with respect to power, electricity, and cost values can aid in better prediction of the grid's potential stability at any instant. The dataset that we use for our study is part of the University of California's machine learning repo. It's a simulated smart grid with 4 nodes having 60,000 data points. 12 different features, including reaction time, power at the nodes, and price elasticity index at the nodes, cumulatively determine the grid stability at each of the instances.
So an important step in studying large amounts of data is understanding what the data looks like. We first looked at the correlation of features so we could get an idea of which features are most important and if they were positively or negatively correlated. The correlation values here show the stability of the grid shares a long relationship with the reaction time and price elasticity values. Naturally, this can be explained. The faster the grid reports what's wrong with it, the quicker people can fix it and restore stability. On the other hand, a stability difference that is induced by a frequency alteration would have a direct impact on the price of electricity at that instance to balance supply and demand. The graph here shows a description of the labels in the test dataset with a 75-25 split. Here, 0 means the grid is stable and 1 represents an unstable grid. On the next few slides, we'll talk about the applications for each of the different prediction models that we have experimented with for the study. So we explored a number of common regression and classification algorithms to predict on stability. We specifically used logistic regression, k-nearest neighbors, random forest, bagging with random forest, XGBoost, and support vector machines. We started by exploring each algorithm without any hyperparameter tuning just to get a baseline of each model's accuracy. To evaluate our models, we used SK-Learn's classification report, which generated F1 scores for accuracy, macro averages, and weighted averages. Initially, we found some immediate success with some of our base algorithms, which kind of suggested to us that hyperparameter tuning isn't going to have a huge impact on improving our models. But we kind of decided that any level of performance increase was worth pursuing. And so we decided to run some parameter optimization on all of our models. Specifically, we experimented with grid search and randomized search. To ensure specificity, we first ran grid search on a wide range of values for our parameters, then slowly narrowed it down to more precise measurements. In the next couple of slides, Parth is going to go more into depth on the specifics of our 6 models and the results that we got from these regression and classification algorithms.
So we began with a logistic regression. We were able to find the proper parameters. As you can see here, those are with an L2 penalty, a lib linear solver, a C of 0.1, and iterations of 400. The ROC curve is shown below, and then on top of that we have like the various precision and recall curves. In that you can see that the scores are pretty good, ranging from about 80 to 85% with both precision and recall, but we were able to improve on this significantly with further models. So here you can see our random forest as well as our bagging. So with random forest, we were able to come up with a further set of parameters with 1,000 n estimators, no max depth, and min sample splits of 2. You can see here that the precision and recall curves are significantly higher. Precision and recall scores are significantly higher, along with a higher F1 score, ranging around 94%, along with a much better ROC curve. And then with the bagging model, we used 200 estimators, auto for max features, and a max depth of 6. And we were also able to achieve a precision recall and F1 scores of about 94. And then finally, we used XGBoost and SVM in the regression and classification side of it. Those parameters are also listed: a minimum child weight, 450 n estimators, a max depth of 8, a learning rate of 0.2, and a minimum child weight of 0.3, gamma of 0.5, subsample of 0.6. So once again, you can see those scores below, about 95 to 96%, even further improving on our previous models. And then with the SVM parameters, we used a linear kernel, a gamma of 0.1, and a C of 10, and we were able to receive positive results, but not as good as previously, with about those ranging from 0.92 to 0.93.
So apart from using regression and classification models, we also tried neural networks to see and use its effectiveness on our data set. So for that, after developing the data loaders with the batch size of 32, we again split the data into train and test data loaders, which we can use in the PyTorch library for the neural network simulations. So for the neural network, we had like 12 features, which should be the input for the first layer, and our output should be labels 0 or 1. So we kept that output final layer as of size 2. And we simulated different number of hidden layers with different parameters, as well as we optimized for epoch at each sides of the network. Once we do that, then we saw the network performance through cross entropy loss. We also measured the accuracy and saw confusion matrix so that we can compare each network with each other. To start with, for the first model, we kept this simplistic model with a single linear layer with 12 input features and 2 output features with ReLU nonlinear activation. And we saw that it is significantly showing good accuracy of 81% at around like 40 epochs. We have seen consistently that after around 40 epochs, accuracy doesn't increase much. So we can say that we can keep our values at 40. Here at the bottom side, we can see the confusion matrix for the predicted and actual stable and unstable conditions. After this, we increased our number of layers to 3 layers. Here we included 2 more layers, and we included the number of parameters as well. and each layer is again activated through RELU. And with just addition of 2 new layers, we saw the accuracy increase of 96%. And we can see, so with this, we were hoping that we will have accuracy increase with the number of layers or number of parameters as we go into more depth. So for next model, we added one more layer and saw that it shows the almost similar characteristics as we expected. It shows around the 95% to 96% accuracy for that model as well. So we went ahead and increased few more layers into our last model. Next, last model, model 4, where we had like 7 layers, and it also shows accuracy about 97% once we run for the number of 40 epochs. And this is the best we got till now. And for this, we can say that we can have better accuracy with neural network in a small amount of time and with small computational power. Next.
So here we can see kind of a wrap up of everything that we accomplished in this entire study. Here you can see all the different accuracies that were generated by the models that we looked into, with the XGB regressor and being a boosting technique having the highest accuracy at about 97%. The second place was a random forest regressor, which we suggest might be a strong candidate due to the binary probability of this problem in detecting stability versus instability. And so those two are likely the algorithms of choice to pursue if we were to go further with this particular study and try to maximize the ability of our model. And going a little bit further on the neural network side, we can see here that the accuracy correlating with the number of layers, we have a positive correlation. The number of layers was relatively successful in each iteration as we added more and more layers to our model. The number of epochs, as we saw in each model from earlier, kind of capped out at about 40. So having anything beyond that didn't really make too much of an impact. It was kind of reaching a point of overfitting the data where we didn't really need to go past that point. And the confusion matrix that we generated was helpful in each stage in deciding how successful each model was. And so basically saying that adding layers was a positive impact on our model as we progress further and how this might impact on a real world application.
The demand for power at any instance of time is dynamic. It has always been there and it always will be. Developing technology and advancement in every scientific genre only makes this demand more complex. Today, we have types of intermittent and complicated loads that were unimaginable when the power grids that we used to use were established centuries ago. It takes now intricate understanding that adaptation to the modern world is the utmost priority for this industry to keep the world running. Prediction of the stability of the electric grid in any state is a sensitive issue. Its implications can be drastic and most of the time irreparable. Thus, it is only after several tests in various conditions that any model developed for this purpose should be deployed. Largely speaking still, several stakeholders in the electric grid deploy traditional mechanisms in order to maintain daily functionalities of power generation and transmission. A quick transition of a stable, large-scale system that has existed for centuries into its highly modern and sophisticated counterpart is absurd. However, this change is now a necessity. Instead, it will be gradual and steady. Two major concerns that the power industry faces in terms of transitioning into a data science-based methodology are the lack of understanding and the willingness to change. Deep learning is a sophisticated subject that many people who have been constantly working in the power industry are not familiar with. Rigorous experimentation, their swift deployment, and an urge towards people in the traditional power field to master new algorithms, and an open outlook towards a transition that can ultimately benefit both ends of the supply chain are the needs of the hour.